In this section of lecture, we are going to study about what is electrochemical cell. Now this is the picture of the electrochemical cell. You can see over here. There are two vessels, separate vessels, and they contain some electrolytes. For example, here it contains the electrolyte of zinc, and here you can see that it contains the electrolyte of copper, okay, in the liquid form. Now these are the two electrodes. These are the two electrodes. So these are the two electrodes you can see over here, zinc electrode and copper electrode, and they are connected with the outer circuit. And as we know that electrons always flow from negative to positive, so the direction of current is from positive to negative. Now you can also observe here in this case, these two vessels, they are connected with the help of the salt bridge. Okay. Now this is the figure, and this is the basic arrangement of a device which was known as electrochemical cell. So from here we can conclude that what is electrochemical cell? The device through which chemical energy changes to electrical energy. That means there are chemicals and they are converting into electrical energy. They gives us electrical energy. That means overall the device which gives us chemical energy from the electrical energy, this is known as electrochemical cell. Then the other name of these are, they are also known as voltaic cell or galvanic cell. So moreover, the electrical energy which we get here, it is measured in terms of EMF, and the full form of EMF is electromotive force. Now proceeding to the next topic. So now here you can see that in electrochemical cell, chemical reactions takes place in the two different compartments, and each of these compartment is termed as a half cell. And this half cell, each half cell contains two different things, that is the electrolyte and the electrode. Moreover, the solution in the two compartments that is converted, that is connected with the U-shaped tube, and that U-shaped tube is termed as the salt bridge. Clear? Now, there's a significance of the salt bridge. Why we use the salt bridge? We can check some of the reasons. Salt bridge connects the solution of the two half cells. Moreover, salt bridge prevents the diffusion of the solutions from one half cell to another. Moreover, it helps in keeping the solution electrically neutral. Okay. Moreover, it prevents liquid-liquid junction potential. That is the potential difference which arises between the two solutions which are in contact. So it prevents this development of liquid-liquid junction potential. It doesn't allow that potential. Moreover, now we know that there are two half cells. These two half cells are known as two different half cells. That is oxidation half cell and the reduction half cell. Okay. So in case of zinc, we see that this is the oxidation half cell because that is losing electron. That means zinc metal is changing into zinc ion. That means when metal changes into ion, then this is the oxidation. Okay, and when the metal gains electron, then it is the reduction. So that in the chamber in which the metal gains, the ion gains electron and become the metal, it is a reduction half cell. Now after that, now we know that what is electrochemical cell, what is the device, and what is the figure of that. Now we learn how to represent an electrochemical cell. So this is the complete electrochemical representation of a electrochemical cell. Here you can see that this is zinc metal, and Zn2 plus, this is zinc ion. That means we write metals and then ions. Now 1 mole, molarity, this is the concentration. That means concentrations are also written over here. Now what are these two vertical lines mean? These two vertical line means they represent the salt bridge. Okay, they represent the two half chambers, that is two salt bridges. Now again, this is copper ion, and its molarity is concentration, and it is converted into copper metal. So when we write ions, there we write the molarity. Okay, there we write the concentration. So in this way we can see that on the left hand side we write the oxidation, because we can see over here in case of zinc this is oxidation, in case of copper this is reduction. So on the left hand side we write oxidation, in the right hand side we write reduction. Okay, So in the right hand side, in the left hand side we write the negative, and here we write the positive. So now the next topic, what is electrode potential? Now next topic we have electrode potential. When a metallic electrode is dipped in its solution, we see that zinc is dipped in zinc sulfate, copper is dipped in copper sulfate. That means any metal electrode, when it is dipped in its salt solution, there's a development of potential difference. Between what? Between electrode and the solution. And this potential which was developed in between electrode and its solution, that was known as electrode potential. Okay, now we can easily see that how will we define the electrode potential. The electrode potential is a measure of the tendency of an electrolyte to gain or to lose electrons. That means it gives us a measurement, it gives us the quantitative measurement that how much electrons are gained or lost in the half cell. So electrode potential gives us measurement. Okay, now next topic we have standard electrode potential. It is generally asked, what is a standard electrode potential? Now when we find the electrode potential of any metal with respect to hydrogen, when we find the electrode potential of any metal with respect to hydrogen, then we get the standard electrode potential. That means, just be careful here, the potential difference developed between metal electrode, this is the metal electrode, zinc, and solution of its ion of unit molarity. We have to take the molarity only one, unit molarity, at a particular pressure of 1 atmosphere and the temperature 25 degrees Celsius, which is the standard temperature. Then this is called the standard electrode potential. And how will we represent the standard electrode potential? And here we write the hydrogen according with the platinum catalyst, then hydrogen ion, then zinc, it is in form of ion, then it is zinc metal. So this is the representation of the standard electrode potential, and its value is 0.76. Okay, so after that we have EMF of the cell. What is EMF of the cell? Now full form of EMF is electromotive force. You can see over here, electromotive force, or we also call it cell potential of a cell. Now we just go thoroughly. In an electrochemical cell, the electrodes in different half cells have different reduction potential. For example, if we have any galvanic cell, we have two different metal electrodes. So they have different potentials. As a result of this, different flow of electrons is seen from the electrode with higher tendency to lose electrons to other electrodes. So every electrode has different potential difference, different potential. So difference in between them. So difference in between the electrode potential of electrodes. See, this is the main line. See, this is the main line. You can see over here what is the definition from here. The difference in electrode potential of electrode, difference in electrode potential of electrodes. Just watch only this section. Okay, clear? So difference in electrode potential of electrode is called electromotive force. Clear? So that means, how will we find the EMF? How will we find the EMF? We find the EMF by subtracting reduction potential of the cathode with the reduction potential of anode. Okay, so when we take the case of reduction, then we have to subtract with the reduction potential of cathode with anode. But when we take the case of oxidation, we have to add both of them. Okay, clear? But in subtraction, be careful. Firstly, we have to write the reduction potential of cathode, then with negative anode. Now this is the definition of EMF of cell. Please learn it thoroughly. And what is the definition? EMF of a cell is defined as the potential difference between the two electrodes when no current is allowed to flow in the circuit. When at the time there is a no flow of current, there is no current in the circuit which was flowing in the circuit, then at that time the potential difference between two electrodes gives us the EMF of a cell. So the condition is that at that time there is no flow of current. Okay, in this lecture we are going to learn what is electrochemical series, the arrangement of metals, in decreasing order of tendency to lose electrons. That means metals are arranged in this way that in the decreasing order of losing electron. This is known as electrochemical series. So the series in which the elements are arranged on the basis of values of electron, so just leave it. So only learn up to electrochemical series. So only learn up to electrochemical series. Okay. The arrangement of metals in the decreasing order of tendency. Okay. So now next, this is the series you can see over here: lithium, potassium, calcium, sodium, magnesium, in this way. And if you see their electrode potential minus 3.05, that means it has very less potential. Okay, and as we go down in the series, it gets the positive values. That means electrode potential is increasing downwards. Clear? Okay, increasing downwards. Then you can see here positive, and here it is 0 0. That means it is for the case of the hydrogen. Okay, so you have to remember this series if possible. Lithium, potassium, calcium. You can see over here lithium, potassium, first group, then calcium, then sodium again first group, then magnesium second group. So you can see that according to the group periodic table we can arrange them. And the third group, aluminum. Okay, clear? So there's a little bit up and downs, but you can learn it. Okay, and in the hydrogen comes after 10 and before copper. So now copper is below the hydrogen. Clear? And now from the copper the electrode potential get positive values. Clear? So now silver, these are okay. Now you can see that there are some things written: increasing tendency for reduction. That means increasing tendency to accept the electrons. Clear? So these are the oxidizing agent, here are the reducing agent. So these are different things, and we learn these one by one. Now what is the definition? The arrangement of elements in increasing order of their electrode potential. We can also say that. That means we arrange all the metals in order of their increasing electrode potential, because on the top we have less electrode potential and in the bottom we have more electrode potential. So this definition is very easy to remember. The arrangement of elements in increasing order of their electrode potential is called electrochemical series. Now how this series is useful for us? Why this series is useful for us? Number one, and comparing the reactivity of metals. So be careful now here in these sentences, because lot of questions are from these application of electrochemical series and mathematical type, conceptual based questions. These are asked in your examination. So be careful for this video. A metal with lower SRP have ability to displace metal with higher SRP. Listen. Secondly, the reactivity of metals decrease from top to bottom. That means the metals which are at the top, they are more reactive. For example, in this series, if you can see, we all know that potassium is more reactive in comparison to copper. That means the elements which are at the top, they are more reactive, and the elements which are in the bottom, they are less reactive. That means reactivity decreases. Reactivity decreases. Okay. So now metals higher in the series are more active, and the metals lying in the lower in the series are less reactive. Okay. Moreover, the elements which are placed above hydrogen, they have ability to displace hydrogen. So when the metals which are placed above hydrogen, when they react with them, they have ability to produce hydrogen gas. Clear? Now next topic, in comparing oxidizing and reducing property. So be attentive for that. It is a very confusing topic. Oxidizing nature increases from top to bottom and reducing behavior decreases in the same way. That means oxidizing nature increases. You will learn only one thing, either oxidizing, either reducing, and make the inverse of that. Firstly, in the first point, we learn reactivity decreases. We learn reactivity decreases, R for reactivity. Okay. Similarly, in the second one, we can see that reducing decreases. So this is again from R. So reducing decreases. So when reducing decreases, oxidizing increases. So you just take the R. So when we move in electrochemical series, reactivity decreases, reducing power decreases. So now it's easy. Okay, so be careful and please note my language, my words here, that reducing property decreases when we move in electrochemical series and reactivity decreases when we move in electrochemical series. Now in the calculation of EMF, now how can we find the EMF? We just subtract the two electrode potentials which are given in the series and we get the electrode potential, EMF, the value of EMF of the cell. Now in predicting the feasibility of the reaction, feasibility of reaction means whether the reaction will happen or not. Okay, whether the reaction will happen or not. In other words, see over here, in other words, 1, 2, 3, 4th line. In other words, we can say that for a reaction to occur, it is necessary that the species with greater tendency to lose electron loses its electron which is gained by the species which have greater tendency to gain electron. So it is not clear over here. Similarly, for a reaction to occur, it is necessary that a species with greater tendency to lose electron loses its electron which is gained by the species with greater tendency to gain electron. So it is just useless, just go to another one, it's not clear. But here we can say that the metal which was before it, okay. For example, in a reaction, I will take one more example. For example, we have a reaction that means K2SO4 and when it react with copper, okay, then copper cannot displace the potassium. But if we have copper sulfate and it react with potassium, then we can form potassium sulfate. Okay, that means if the metal which was above in the series, it comes in contact, the reaction will happen. And clear or not? No. For example, we have a reaction. I will take a space over here. Wait. Listen, we have a space over here. See, for example, we have a reaction like this. Copper sulfate and the metal potassium came in contact. Okay, then reaction with fissile, K2SO4 is formed. Okay, and copper is reduced because potassium is more reactive than copper, because potassium comes on the top of the electrochemical series. But for example, we have K2SO4 and copper came in contact. Copper is in the downward position. Clear? So it is less reactive. So no reaction. Clear or not? We have a compound and there's a metal which came over here which is more reactive. For example, I have an idea. You have a friendship with someone. A person came who is very jolly, who is very impressive. Your friend gets attracted with him and your friendship will break. And for example, you have a friend and a person came over there who is not so attractive and your friendship will not break. Clear? If the substance which came in contact is more reactive, then the reaction is feasible. I think it's clear to you now. Okay? So this is known as feasibility of the reaction. Understand? Now it's not useless. Now in protecting the metals from the corrosion, it is done through